All right, Jim, I think we can kick it off. I will let some people in. We still got some people joining, so I will let them in as they come. Again, everybody, thanks for joining. This is our ninth Ambient Academy course. This is winter operation of air source heat pumps, and this is with Jim O'Donnell, who's one of our sales engineers at HC9. He has done some great work for us before with some of our other companies, so we're very excited to have him back and do another presentation for us. So just a couple things before we get started. You do not have to enable your camera if you don't want to, but you are able to. And you can also raise your hand to ask questions free with through the Teams meeting, but you can also unmute yourself. We have a pause or break, and you can ask some questions there. When you join the call, just make sure you've used your same full correct name that you've used in the Ambient Academy account online, just so we can make sure that you get your PDH certificate correctly. All right, Jim, thank you again for doing this for us. So I'll pass it off to you. I'm going to stop sharing my screen here. You can take it over.
Okay. Bear with me a second. Okay. All right. This is always the most nerve-wracking part is getting the technology the technology information or the technology figured out. So anyway, my name is Jim O'Donnell. Thank you for the warm reception, David. There's my contact information. I work for HC9. I'm based out of Philadelphia, Pennsylvania. There's my contact information. So let's get started. Just today, wanted to go over winter operation of air source heat pumps. Air source heat pumps seem to be, or just heat pumps in general, seem to be the wave of the future that's upcoming. Just today, agenda items to go over. Just going to do a quick, simple review. Going to go through quickly the benefits and drawbacks of air source heat pumps. I have to just write a note to myself that I often call these air side heat pumps instead of source. I'll spend the most part of the presentation going through applications during winter time. Some different scenarios, different selections that I've done over the years, and then just a quick comparison of air source heat pump versus water source, a couple slides on that, and then just my 2 cents of the future direction that air source heat pumps seem to be taking. So let's get started. First with the simple review. This is an old carrier slide, just a package. We're going to talk about rooftop units, package rooftop units, contain filtration controls, airflow. Our DX system is still doing cooling and dehumidification. We're going to now incorporate heating, and then we'll still have heating in our heat pump, but these could be considered to be supplemental or auxiliary heating. Here's another just old carrier slide from past work where I used to work, but this is just a simple breakdown of your refrigeration system. Essentially what we're doing is on the right, we're taking the indoor heat from the indoor air, we're dumping it into our refrigeration system, and then we're expelling it outside. In the heating, we're doing the opposite. Even though it's cold outside, we're taking the heat or energy from the outside air, we're dumping it or running it through our refrigeration system, and then discharging it or expelling it to our via our indoor coil to our airstream that gets distributed to our spaces that we're serving. And then the other benefit in the heating mode with heat pumps is that you have a compressor. That compressor, its inefficiency is essentially it's adding energy/heat to refrigeration system to our refrigeration system, and then therefore that energy also gets expelled to the space. Just a quick review of different additional items that are used with a heat pump versus a cooling oil system. Just from left to right, we have a suction line accumulator. We have a 4-way reversing valve. On our outdoor coil, we have a second thermal expansion valve. And then along with that, a thermal expansion valve, we have a distributor cap as well as the spider piping. And then our filter dryer goes from a single, flow to a dual or bidirectional flow filter dryer. These items are relatively small, cost-wise in nature, as you can see. They are also just standard refrigeration accessories. Here's just a cutaway view of a condensing section, just showing where those units are approximately located. You can look at that afterwards if you like. And then just the other thing associated with rooftop units, the benefit of them is obviously pre-packaged and pre-canned, pre-engineered controls. Essentially, you're taking the same controller for a conventional unit. You have your fan, cooling, dehumidification, your same sequence of operations are all essentially the same. I just highlighted the heat that you get a little bit more complicated when you start adding the air source heat pump with your supplemental heat, and then we'll talk about defrost, et cetera, like that. And then from a control perspective, the main thing is that we've added a little thermostat there shown on the condenser coil for protection. So it serves as a freestat, and then it will also serve as help with lockout and also our defrost mode that I will talk about more in depth. All right, the benefits and drawbacks of air source heat pumps I'll talk about next. Everybody's familiar with the trend of the world of going towards electrification or decarbonization. What we're trying to do, or people are trying to do, is reduce the use of fossil fuels and increase the use of electric. You're seeing this with automobiles. You're seeing this with air conditioning units, et cetera, like that. Trying to reduce carbon emissions and greenhouse gases. The next two items are just some headlines that I took, probably from a couple of years ago, just with different entities trying to reduce the use of fossil fuels and increase the use of electric heat. And then just, what's, I wouldn't say funny to me, but just the federal government I've seen it wants to ban gas stoves, and I just laugh to myself that, I love cooking on a gas stovetop versus electric. I'm going to have, if I have to switch to electric, I'm going to have a lot more, food that's going to be burnt on the inside and raw on the inside. But anyway, that's my lack of cooking skills, and thanks to my wife, I'm safe. All right, air source heat pumps benefit with energy savings, especially in heating mode. There's a efficiency performance called coefficient of performance, where basically, like any efficiency, it's how much output you're getting versus input. For this situation, it's how much heating we're getting outputted versus how much energy we're putting in. So an air source heat pump has a COP of a range of approximately 2 up to 3.8. As a comparison, electric heat is 1.0. And then if you do have gas heat, whether your AFU efficiency is 80% or 90 or 92, so that's your range of what your COP would. So simple payback analysis, this might be a little bit dated, but once again, just wanted to do something using an Excel sheet and bin temperatures. For heating, we would use an air source heat pump instead of gas. Just these were my inputs. I highlighted the electrical cost. I always try to do things in items of 10 just so they can be ramped up or ramped down. Those values are probably from a couple of years ago. Not really sure if they're really accurate today. But basically, just if you have a simple office, once again, I'm in Philadelphia, so I'm using those bin temperatures. A payback of approximately 5 to 8 years. Will vary on so many different inputs, but usually a payback of less than 7 years is attractive for items. And then also too, if you look at greater operation, you will obviously have a more operating hours turns into a quicker payback. These are just rough numbers that I did with a simple Excel spreadsheet. Also, with air source heat pumps, the other benefit is that you'll have better comfort of your space at milder ambient temperatures. This is once again comparing an air source heat pump with a gas heat. There's my tonnage in the unit. This is what I came up for a design of my heating system. Outside air temp of 0, maybe my return air temp should have been 70, 57 instead of maybe those room conditions. Mixed air temperature of 54. Therefore, my gas heating or my heating system is about a 40-degree rise. Now, what happens, that's when you design your heating for your worst conditions at your design temperatures. But what happens when your outside air temperature is at more, more common outdoor temperatures. So this example here, I just used 42 and 47 just to highlight that my mixed air changed from 55 up to 67. So if I went back to that gas heater, where my gas heater is sized for about a 40-degree temperature rise, I'm going to have a leaving air temperature of approximately over 100. If my space is at 72 or 75, that 170-degree air is going to obviously be way too warm. Also, too, if my ambient temperature is at 47, 42, doesn't really have that great of a heating requirement. So just question, a gas heater is going to be able to turn down properly, or is it going to cycle on and off, which you don't want to do. But if you do have an air source heat pump, you'll be able to have a modulated compressor, whether that modulating compressor is a digital scroll or a VFD. You'll be able to accurately dial in your leaving air temperature, to your space temperature to once again improve your comfort conditions in your space. Now, the limitations of air source heat pump, the first one I want to bring up is that your heating capacity in the wintertime, essentially your heating capacity gets greatly reduced. Equipment ratings from ARI or AHRI are typically done at 40, for heat pumps are typically done at 47 and 17-degree ambient. This is just a graph, probably a VRF graph actually, that shows just as your ambient temperature drops, your heating output also decreases. And then just back to my 15-ton example with these airflows. At 47 degrees, I'm getting 170 MBH, or temperature rise of about 28 degrees. But if it's 17 degrees out, I'm getting 100 MBH, which is about a 40% reduction. So just keep that in mind when you're designing for your heating system. You'll design for that 17 or 10 or once again, Philadelphia's design temperature is 9 or 10 degrees ambient. A lot of engineers want a safety factor, so in our territory, some people will use 0. Now, the other thing you have to be cognizant with air source heat pumps is that they do contain a defrost mode, and this defrost mode will occur during the wintertime. On the left there just shows a pressure P&H diagram for your refrigeration system. Want to make sure that you're understanding that in the heating mode, our outdoor condenser coil is now the evaporator, and then our indoor evaporator coil is now the condenser. So as the Q and the Q to me refers to energy. So what we're doing is we're removing the heat from the outdoor air. We're dumping it into a refrigeration system, and then that refrigeration system is circulating, pumping with our compressor, et cetera, like that, and then we're discharging the heat to the indoors. Now, what will happen when the outside air temperature is at 40 degrees and it starts getting lower and lower? What will end up happening is that our refrigerant temperature, slash pressure will end up dropping. We'll end up eventually getting to a point that the heat pump is run so much, the air temperatures have gotten so cold that eventually your refrigerant temperature will get too low in heating mode, and the unit won't be able to safely or properly operate. So what will happen is the rooftop unit or your split system, actually your air source heat pump, will activate what they call, what's referred to as defrost mode. All right. So what is defrost mode? Defrost mode is essentially taking the refrigeration system or taking the rooftop unit and warming up the refrigerant so that it can then go back into heating operation. So first what it will do is we'll turn off the air source heat pump and heating operation. The second thing, I took this right out of a sequence operation. It says reversing The reversing valve will switch the opposite direction. That's well and good, but just realize what that's saying is that the heating unit is now going to cooling. We'll end up warming up the refrigerant by using two items. The first is they'll run the compressors at 100% capacity to add as much heat as possible. And then in addition, we'll heat the refrigerant that's in the airstream by, with the combination of return air and outside air. And then also too, what will happen next is that the rooftop unit or the split system will turn on its supplemental auxiliary heating. This, as I said, can be gas, steam, electric, et cetera, like that. And then we'll also activate a defrost timer that typically is 10 minutes long before it goes allowed to go back into heating mode. Want to just emphasize once again, as that box in the center says, when you're in defrost mode, your air source heat pump is not in heating. All right, you got to make sure you realize that, and it is going to occur. So let's talk about how the how the manufacturers or designs are just trying to minimize the limitations of your heating capacity as well as your defrost. What they're trying to do is operate your air source heat pumps with lower ambient temperatures, producing more output heat. So currently the design, I'll say, is averaging about 0 degrees for ambient. In the future, they are working towards minus 20 ambient. So what has been done? First off is that just with technology and testing and stuff like that, the equipment manufacturers as well as compressor manufacturers have better testing, better design. It's very critical to match the performance of your evaporator and condenser coils. They're generating a much more accurate operating envelope with this air source heat pump in heating and cooling mode. Next, stealing sort of from the VRF's world is that they're changing, on-off or digital scroll compressors to VFD compressors. If you have a VFD compressor, you're able to overspeed it from 60 hertz up to 90, slash 100 hertz. This will produce additional heating output. And then inherent with VFD compressors versus the old kind of mechanical ones, you'll have quicker response times, more accurate capacity control, as shown on that graph there. And then just, lapping on the right there, there's a compressor with its VFD next to it. And then there's this enormous electronic expansion valve that really isn't that big, but just wanted to make it bigger, that you're changing from a thermal expansion valve to an electronic expansion valve associated with the VFD compressor. Next two items, the first one that I kind of minimized is just, they're putting in better condensing system design. In my mind, once again, from the VRF systems typically have their smaller tonnages, for their condensing coils, or condensing systems from like 6 up to 14 tons. And what they end up doing to reduce the defrost is that they provide additional circuiting on their condenser coils. This might not be so feasible if you have like a 30-ton unit. You have a 30-ton unit with, say, two 15-ton refrigeration systems. It might be difficult to manipulate or just redo that 15-ton condensing unit into, instead of one big coil, into 2 or 4 smaller ones. And then lastly is just better controls, as I said, with the VFD, changing the electrical, mechanical to direct digital controls. And then another term that's come up the last couple of years is adaptive defrost operation. So this is just, once again, using more accurate DDC controls. They're also, what they end up doing is, instead of just the defrost cycle running for 10 minutes, they actually track how long the defrost cycle runs. And if they can, if they're realizing, okay, over time my defrost ends up cleaning itself or resetting itself in 6 minutes or 8 minutes, the controller will reduce that time frame to reduce the length of the defrost. Once again, just want to emphasize that when you're in defrost mode, you're not heating, so less defrost mode means more heating output. All right. Now the next section I'll try to spend a lot of time with it is applications of the air source heat pumps in the wintertime. Took a stock picture or for what I can't remember where I got it, but basically just trying to demonstrate that there's a lot of juggling or decisions or applications, items that you have to kind of make a call on depending on what equipment you're using, probably what manufacturer is available, what they have for options, what's your actual application, the space that you're serving, sequence of operations, et cetera, like that. So first, just want to compare if you have a cooling only unit versus an air source heat pump. There's the conditions in my entering air temperature there. Just if you compare just a cooling only unit versus an air source heat pump, what will end up happening is that your leaving air temperature in the cooling will probably slightly increase. I attribute this to what I would expect is that you're adding specialties to refrigeration system, such as the suction accumulator and that four-way valve. So you'll have a little bit more inefficiencies introduced to your refrigeration system. And then the other thing to look at is in the air source heat pump, maybe you have a comparison or available digital scroll versus VFD compressor. There's a little bit better performance on the VFD compressor, but then just in my example here, what ended up happening was my VFD compressor had a 6-row cooling coil available versus a 4-row. So, obviously more metal, more heat transfer is available with the 6-row coil, so you would eke out a little bit more performance. So just realize that your performance might change. I really consider this to be minute and slight that's not going to disregard or just eliminate a section of an air source heat pump because my leaving air temperature and cooling rose a half a degree, et cetera, like that. Next, just want to talk about just your heat pump, your air source heat pump output tables. This one here is just typical of what I've seen. On the left, you have outside air with different bin temperatures and 5 degrees. For this application, I had about 25% outside air, so there's the equivalent mixed air temperature. Next, going from left to right, we have our leaving air temperature. Want to just emphasize that this is the leaving air after the air source. The next two tables are heating capacity. There's an integrated that I'll explain next, and then also there's our coefficient of performance. So just want to emphasize or just reiterate once again that as our ambient temperature drops, we're going to reduce our heating output. You can also see that our coefficient of performance has also been reduced. Now, what is integrated heating capacity? If you do a comparison at the different bin temperatures, you can see that the integrated heating capacity has a lower output capacity versus the standard heat pump. What the integrated heating capacity is doing is that it is partially reducing your leaving air temperature, your capacity, due to the defrost operation. So what ends up happening is we end up adjusting our actual leaving air temperature in the chart here is reflective of the integrated heating capacity of our air source heat pump. Now also, is supplemental heating required? Going back to our chart here, I'm going to just tell you that probably almost always, or right, Rick, we've done this every single time with auxiliary heat. All right. So once again, just looking at as our temperature gets outside here, 27 and 12 degrees ambient. This is once again done for the Philly market that I primarily work in. You have our mixed air temperature at 53 and 5046, and then you have a leaving air temperature at 84 versus 72. So what will happen is issue number one is that our leaving air temperature could get too low. Say if it's 12 degrees out, we had a space at 75. We would want our leaving air temperature to be approximately 95, 72 degrees is going to be too low. And then issue number two that I'm going to further explain is that refrigerant defrost is going to occur. So once again, the air source heat pump is not heating. So that these two temperatures here, would expect that during some time of its operation, the unit's going to go into defrost mode to try to warm up the refrigerant. So planning for defrost mode, once again, back into Philly. I live near the Rocky statue in downtown Philly there, but looking at just bin temperatures. Bin temperatures, if you're not familiar with the definition, number of hours per year that the average outdoor temperature of the location was contained in a temperature band or bin. First learned about these that item or that energy. I worked at a consulting engineering firm, and they had a division that did energy studies, and so we used to do before probably before calculators, maybe not that long ago, but anyway. But so sorry, I digress. So if you're looking at Philadelphia, if you have 24/7, 365 operation, just from the bin temperature is about 25% of the time you're below 37, and 2% of the time you're at below 17. But then if you compare it to an office, you'd still have approximately 15% of the hours below 37 degrees where you should plan or just understand that defrost is going to occur. All right. Okay, thanks. So here, so what are we going to do to try to minimize our defrost? So additional heating solutions, you can add heat to the rooftop unit. You can position this in the reheat position where you'll have your air source heat pump as your first stage, your supplemental heat as your second. And then the other thing that's becoming a little bit more prevalent is to add a preheater just to the outside air. Other items, you can oversize your rooftop unit. Instead of designing traditionally for the cooling load, you can design it for the cooling load. Can add an energy recovery device. This is showing just a wheel here. And then obviously external heating systems as duct heaters, et cetera, like that. And then just my observation is that item number 2 and number 4 kind of, if you work in VRF, you should be familiar with these concepts, and then maybe, energy recovery units also for item number 3. So back, what's your application? Do you have a new system that you're designing? Is it a replacement of existing? Are you limited by electrical service? What's the weight of the existing unit versus new? What are your operating hours for those, radically different spaces there? Is it process or comfort cooling? And then also too, what type of auxiliary heat do you have available? Other items about your application is what's your percentage of outside air? What would be your sequence of operation? What leaving air temperature that you're looking for? And then also too, associated with the DOAS system, essentially what's your leaving air temperature that you're going to be considering with those different options there. All right, so what's an acceptable leaving air temperature? Once again, dependent on your system. And then what I want to look at or just make you understand is that what's the leaving air temperature that you're getting from your rooftop unit when your air source heat pump is operating, and then also when your air source heat pump is not operating, which would happen during defrost mode. So let's go a couple different scenarios of projects that I worked on or selections that I did, and then just expanded for the different options here. So first, looking at the reheat solution, where you're adding auxiliary heat. This one here is going to be for electric heat. So here's our output of our unit, 15 tons at those ambient temperatures. Here's our mixed air temperatures with those conditions up before, once again, using Philly for my calculations here. These are our mixed air temperatures before our air source heat pump turns on. And then for my computer program, these are the leaving air temperatures of the air source heat pump after the after the air source heat pump is in heating. All right, so we're going to assume a design with the leaving air temperature of 95. So if I'm going to use as my entering air temperature 65 that the air source heat pump is operating, that comes out to a 50 kW heater. But then if I look at my heating operation with my air source heat pump not operating, it's in defrost mode, Therefore, that turns into a larger heater. If I looked at a 60 kW electric heater, this was my leaving air temperature. And then if I looked at an 80 kW electric heater, that was my entering air temperature. So those are your associated electrical, service that's required. And then just want to point out that when you have a unit with electric heaters, depending on your tonnage, et cetera, like that, you have options for different sizes. They're usually in about 10 or 20 kW increments. So for this unit here, we'd be looking at a electric heater approximately in that size. Now, if you have an electric heater, you have to check your electrical circuit. Just realize that you have two electrical circuits operating at the same time. Your refrigeration system, your electric heater, and then with the unit, you have three different control sequence of operation and power options available. So back to my 15-ton selection with that 60 kW heater. Option A is with simultaneously operation. This is when you allow your refrigeration system and your electric heater to operate at the same time. This usually results in your largest electrical service. You do have to consider defrost mode. Option B is called, or not, I'm not sure if all manufacturers have this one available, but you can select a maximum MCA of your electric heater that your unit will not exceed. Maybe you have an existing unit with a certain MCA, and you don't want to go over the existing MCA, because therefore you'd have to pull new wires from your circuit breaker out to the unit. They both can run at the same time. You do have to consider defrost mode. This example here is probably a bad example, but my MCA, was the same as that. And then I will say that option B is not really ever selected. This is only done on very large rooftop units with electric heat, just because, say you have 208 with 60 or 70 tons, you end up with a large electrical service. The other option is, I'll call it IMC, where you can have an either or operation. You can either run the refrigeration or the electric heat. You can't run them both at the same time. This has the smallest electrical service requirement, obviously, because you're not running both items. Typically what happens is you end up locking out the air source heat pump so that it can't go into defrost mode below a certain ambient temperature. Just realize once again that your electric heat cannot run in conjunction with your refrigeration system. So if you compare the option A versus option C, you can see the difference in the electrical service. The simultaneously option typically has greater energy savings because you're essentially running the operation. You're running the air source heat pump more than you would in the other scenario. This is, a lot of times is very dependent on, this is a new project versus a replacement. Would say that new, we end up doing simultaneously heating all the time. And then if we have replacement, we, it's not 50-50. Once again, it's probably mostly simultaneous, but there are situations where it becomes critical of the electrical service. Now, if we're taking an existing unit that has gas and then switching to electric, just running a couple different scenarios. This is a 15-ton existing unit with that electrical service. If we had gas heat, our MCA went up, maybe some changes to our compressors, et cetera, like that, over a span of 10 or 15 years. But what becomes problematic is that if you take an air source heat pump and then you change it to electric heat, you can see the difference of the electrical service is extraordinary. It's much larger than the existing service. And then I did I don't want to say a sister prezo, but a dual fuel presentation back before this one. And I did have an example of an 8-ton unit that had a similar situation, that the existing unit had that electrical service for a gas heat, and then switching to an air source heat pump plus electric heat is much larger. All right. So if we're using gas heat, Once again, you're going to compare simultaneously versus either or. Usually the simultaneously has smaller electrical service. With the option C, the either or, only one of either the gas heat or electric heat can run. If we're using 0 degree as my design temperatures, our gas heater would end up with this output. And then if we have it where the air source heat pump is not operating, therefore we have a lower mixed air temperature, we'll have a higher heating requirement. And then just want to point out too that traditionally gas heaters have much less options in terms of increments for heat. So this was a 15-ton unit that had 195, 293, or 390 input. So once again, you're kind of forced either with one or the other. Would say that just to go from the 290 to 195 gas input is I would say chump change, but it's a small add to go to change that. Whereas electrical service, because you're often changing the MCA and a breaker or circuit breaker size on the unit, ends up sometimes more problematic. All right. Other option, just quick, if we take a preheat the outside air with electric as a preheat, this is only for the outside air. So this example here, just using a 20 kW heater to heat the air from 0 up to 41. Next, with our mixed air temperature before our air source heat pump, we get a mixed air temperature of 62.2, leaving air temperature of 73.2. So if we wanted a leaving air temperature of 65, we could put in a 40 kW leaving air, to get our leaving air temperature. And then once again, just want to point out that, hey, 20 plus 40 equals 60. This was the same kW as the last selection. Option number 2 is oversizing the rooftop unit, sort of stealing this from the VRF industry. Wanted to compare a 15-ton versus a 20-ton. These are performance at 15 tons. These are the performance at 20 tons. You can just see at the 17 and 0 degree, we're getting additional heat, a little bit higher temperature. And then want to also compare, just think about, hey, is my cooling load now oversized? With a 20-ton, what's my part load capacity? Just always be careful with VFD compressors. The typical VFD compressor has a turn down of 30 to 40%. So it depends on how many compressors you have in your unit, et cetera, like that. So just, once again, be careful of your turn down. For this example here, you had a 15-ton with the leaving air temperature of that, and you had a 20-ton with the leaving air temperature of a little bit lower. Once again, in my opinion, it was 2 degrees. You weren't really oversizing the unit anything drastically or anything that could really get you into trouble. Next, let's look at adding an energy recovery unit. That energy recovery unit is going to recover heat from your exhaust air temperature and raise your mixed air temperature. Back to this unit here. If you have a unit without energy recovery, here's your performance. If you add an energy recovery wheel, as expected, your leaving air temperatures are going to increase. At 0 degrees, you're adding that much energy or heat into our system versus the heat pump. Now, once again, are we oversized now in cooling? We've got a 15-ton unit as well as a 4-ton ERV. So a 15-ton unit with our ERV with that leaving air temperature, maybe it's a little bit low. Just as a comparison, if I looked at a 13-ton, it's probably the same cabinet size, maybe a little bit tiny, probably the same fan system. Controls are obviously the same, maybe a little bit, there's a smaller refrigeration system. Once again, just those are our leaving air temperatures, probably could be acceptable depending on your application. And then just your heating capacity, for 15 to 13 ton, in my opinion, had a negligible difference. Also, with your energy recovery wheel, you have to be aware that there is a second defrost mode associated with the energy recovery wheel. What will happen is if our outside air temperature is too low and our return air temperature, I guess, is too moist, what will happen is as the wheel turns and the air from one airstream enters the other, the moisture on that wheel could, will form and condense out. And if our, line drawn there on the system crosses over our saturation line, and it's below 32 degrees, we'll have defrost. So back to our 15-ton unit, with those outside air and return air conditions from the program, we end up demonstrating that, hey, my exhaust air temperature is below 32. We're going to end up with defrost on our energy recovery wheel at certain situations. Just playing devil's advocate, once again, just looking at different applications. If I raise my outside air temperature to those conditions, then therefore my exhaust air temperature is going to be above 32 and not have defrost. Just realize when your unit energy recovery wheel goes to defrost, the timer is much shorter duration. There's different types where they can jog. Jog's a nice name for on-off control. Or if you have a VFD on your unit, what you're basically doing is slowing down the wheel, you're reducing your heat transfer. You're essentially using the return air to warm up the media of the wheel. Other solutions for the defrost mode is you could implement or use a bypass damper. You might already have it there for economizer mode, and then you could add an electric preheat to raise your outside air temperature above that dew point temperature. So just looking at a 15-ton unit, we have these conditions. If are comparing the mixed air temperature after the energy recovery or without the energy recovery, once again, you'd have to be concerned about what's your leaving air temperature that you're looking for. So what auxiliary heat to use with our energy recovery wheel with these mixed air temperatures, those conditions, if I'm designing for a 95-degree leaving air temperature, my smallest heater would be with nothing in defrost. We come up with an output of 102 MBH. And then our largest heater would be if both defrosts occur at the same time. Probably not going to happen, but you never know. Anyway, that gas heater would turn out to be 207 MBH, sorry about that. And then once again, for our gas heater, we probably just automatically size to the 293. The electric heater, once again, we have a little bit more options, but available for that. Last couple slides to the application is let's look at just additional heating solutions. This is 1B where you're adding the outside air electric preheat as well as the energy recovery wheel. I switched this one to 100% outside air. So as there's the path of our outside air as it gets heated. These are some appropriate temperatures. Start at 0 or 10. Size your electric heater to 35. That 35 is above our requirement or just any danger of that energy recovery wheel going to defrost mode. The leaving air temperature from our air source heat pump, and then just highlighted the 90 or 100 with our reheat. And then once again, this is DOAS, so maybe you're providing just neutral air. Maybe your leaving air temperature, you wouldn't need that reheat to be added, or maybe you want to just put it in there for situations where your air source heat pump could go to defrost. All right. Just a quick comparison, a couple slides, this air versus water source. Just a water source, what you're doing is you're using a water or glycol solution in lieu of air. We're taking the same heat transfer from our source. We're just using water, so water to the refrigerant into our space in heating, and then the opposite happens in cooling. We're cooling the air, dumping the energy into our refrigeration system and expelling it, outdoors or to a lake, et cetera, like that, for our heat rejection. These are common applications where you have a lot of multi-space, lot of zones such as offices, education, et cetera, like that. Just once again, a cutaway view of a water source heat pump. So in cooling mode, you're essentially running your air across your evaporator. You're dumping that energy into the refrigeration system. You're then expelling it in the center there with just a source of water from a loop. The opposite happens in the heating. You're taking the energy, the heat from the source. You're also adding, you want to highlight once again, you're adding the energy, heat from the compressor, and you're discharging it into the space. What ends up happening is that heat exchanger changes to a water-to-water heat exchanger, which could be a coaxial heat exchanger shown there, refrigerant and tube in with other, as well as a plate to plate on larger sizes. Excuse me, here's just a typical water source heat pump arrangement. You have multiple zones with individual heat pumps. You have a circulating pump, you have distribution piping. You have a boiler where you're adding heat. You have a fluid cooler where you're rejecting heat. Once again, just want to emphasize this doesn't have to be strictly a boiler or a cooling tower as kind of depicted here. And then just with the water source heat pump, you obviously have, or just you have a lot more options in terms of your available systems there. All right. And then just a quick comparison of pluses and minuses of water source heat pumps. Because you're using water, it's typically more efficient than air source. It eventually comes down to your heat transfer with wet bulb temperatures versus dry bulb temperatures. You'll be able to get much more redundancy with smaller units. You have more flexible with the different types of units that are available. The disadvantages is traditionally does have higher first cost. Supplemental heating can be problematic, or just with your boiler, or do you have to add it at your system and stuff like that. And then just realize that obviously if you have water source heat pumps that are in spaces, you have to be careful about cognizant that the compressor does run. The compressor could potentially make objectionable noise. Air source heat pumps are lower first costs overall. You don't have to run all the piping around, et cetera, like that. If it's a rooftop unit, it's very easy to add supplemental heating. There's obviously much less concerns about noise because these are typically in remote locations. Disadvantages, you have less options for indoor-outdoor units. They can't be as large. And then obviously we talked about in the wintertime, you have to be cognizant that you will have a capacity reduction, and you do have to plan for defrost mode. Just wanted to touch on maintenance, probably cherry picking some of this, but obviously the water source heat pump has, the additional thing of water treatment. You do have a control system that's pretty simple, but you do have a control system for the loop. And then from air source heat pump, it's obviously less maintenance for an air system versus water. And then you'll have, from a maintenance perspective, traditionally you'll have less units to look at for maintenance, but typically the DDC is more complicated than a simple water source heat pump that's 2 or 3 tons that has heating, cooling, maybe hot gas reheat, et cetera, like that. And then, coming to the end here, just a future direction of air source heat pumps. This is the world according to, what was that book, Garf or something like that, but this is my, old-fashioned or just old fogey take on things. Just current status, once again, looking at rooftop units. These could probably maybe be also applied to, split systems. Right now, the capacity of the air source heat pumps is around the range of 40, 50, 60 tons. This probably changes per manufacturer. We'll also say this is what I'll call just traditional pre-engineered units. An example would be, Aeon, Carrier, et cetera, like that. There are custom refrigeration manufacturers. The ones that come to mind are Annex Air, Nortec, probably some other ones as well. That probably could go with larger tonnages for air source heat pumps. Just they're currently using digital scroll and VFD compressors. Your defrost gets activated at those, ambient temperatures. I like to use, people make fun of me because I like to use the word ish for everything as approximations. And they're like, you're not supposed to do that. You dummy, it's not proper English. But anyway, heating performance, typically it's down to about 0. Below that, you end up, not being able to get selections because your your ambient temperature is basically too low. Future direction for rooftop units, probably going to increase tonnages. You're going to increase the use of VFD compressors. That seems to be the way of the industry, period, with better capacity control, better efficiencies, et cetera, like that. You'll have less defrost operation by improving the heat transfer, et cetera, like that, and they'll increase the heating output down to lower temperatures, and then probably also increase the heating output currently than where it is. And then actually the big change that's coming, January 1st of 2025 is the refrigerant HFC 410A is going to be, phased out by the EPA. It seems that rooftop unit manufacturers are most of them are going to 454B. This is being driven by the requirement for a lower, first they hit the ozone depletion, now they're emphasizing or looking at reducing global warming potential. All right, so just in summary, just with air source heat pumps, went over just a quick review of what they are. You're seeing the industry produce or just go towards a trend of not selecting or replacing or designing units with gas heat that's using fossil fuels. You're using more air source heat pumps with electric heat. You want to be careful that you have to design for, to be cognizant for designing, very careful of designing the air source heat pumps for your design winter temperatures. Just your applications, just once again, tried to give you a couple of examples of, what if or hypothetical situations that you might be faced with. Would say that you should always, instead of just sending your salesperson a selection, you should talk to them about the application that you're looking for. Electric heat, you have to be cognizant of obviously have a lot higher electrical service. And then if you add in the use of or need for defrost controls for that. And then the last thing is just speculate on a future direction. And then once again, want to emphasize that 410A is being phased out on deliveries of new equipment on January 1st, 2025. That's associated with, I'll call it rooftop units and, items with scroll compressors, rooftop units, and, split systems, 1-to-1 or 2-to-1 split systems. Would be applicable to chillers, but I feel like the world of chillers has already migrated to the new refrigerants, so it's not applicable. And then just want to also point out that the refrigerant conversion for VRF systems was granted an additional year for the phase out. So that for the VRF phase out is 1/1 of 26. All right, so thank you all for attending. Take it for questions now. Have to work out the PDHs that are available for this presentation. And then just want to emphasize or just publish that the upcoming webinars that I'm pretty sure I'm tasked with looking at to review, the next gen of A2L refrigerants. Have to figure out what to do for the Thursday, the May presentation. And then on question 15th, just David Golden, that's like a Saturday. And I don't think people want to attend on that, but just was looking at, we're starting to get a lot of questions from consulting engineers about the ratings, the ARHI ratings for DOAS units that's changed from the traditional EER, IPLV, SEER kind of stuff or whatever. Alrighty, thank you all once again.
Jim, thank you so much. And I just want to give folks the opportunity to ask any questions. If you did have any, you can either raise your hand, you can type it in the chat, and we'll give folks about another minute or so here. If you have any questions, you can certainly do that. And thanks for joining, everybody. So we'll leave it open here for another minute if you have any questions. And if not, have a great day, everybody. It's like Jack Lowe has a question. Go ahead.
Hey Jim, thanks for the presentation.
You're
I was
welcome, Jack.
wondering, you briefly mentioned the VRF systems, how that's a little bit better than when it comes to operating in the winter or low temperature environments. Maybe you did elaborate on that, but I wasn't sure if, maybe I missed something there. Can you kindly get into it just a little bit, without starting a whole thesis, but just
Sure.
see.
Okay. Yep. I mean, first off, I'm not up to date on experiences or using a VRF. I'm going from previous jobs or just following the industry. So my understanding is that VRF systems, from a heating perspective, are able to not have two things. They don't have such a large D rate versus traditional rooftop units. I would attribute that to the VRS systems overspeeding the compressors to running them at 60 or 90 and 100 hertz instead of 60. And then the other thing that I would attribute that to is that they have better defrost controls. In terms of on the condensed, they probably have all the same requirements for temperatures, safeties, et cetera, like that. But just my recollection is that you have a VRF system. They're traditionally sort of like rectangular and tall, and they have condenser coils on two sides or all four sides. And what they do is they circuit the condenser system so that one face or two faces of the condenser coil is on a different circuit. So when there is a call for defrost, they end up being able to only defrost two sides or one side out of four of the condensing coil system, and then the other unit, I don't know if it's still in heating mode or it's just not as bad. So that would be my 10-cent understanding of of the better ability of VRF systems in terms of winter operation. All right.
All right. Do we have any more questions? I'm still responding to a couple on the chat here, but you're more than welcome to raise your hand or anything else. All right. Well, I will send this one last response here in the chat. Otherwise, everybody, thank you so much for joining. And Jim, thank you as well for doing this. We look forward to your next presentations coming up. So thanks everybody for joining.
Thank you.
Thanks everyone.
Thank you, everybody. Have a good day.